All right, for 21E, I've decided to split it into three parts. We are talking about rational functions for all three parts. The first part, we're going to talk about how to graph or sketch a linear over a quadratic. The second part will be quadratic over quadratic, and the last one will be quadratic over linear. So let's start by looking at just an example of a rational function where the numerator is linear and the denominator is quadratic. The first thing that I like to do when I have this is I like to factor it as much as possible. So that would be 3 times x minus 3 on the top, and then on the bottom that's a quadratic that factors into x minus 2 times x plus 1. Alright, and I like to do that because I know I'm going to use this factorization to find certain aspects of the curve. So I'm told to determine the equations of the asymptotes, find the first derivative and determine the position and nature of any stationary points, find the x and y intercepts, and then after doing all of that we're going to sketch the graph. So we start by looking for vertical asymptotes, and I do that by setting the denominator equal to 0. So now that I've factored the denominator into x minus 2 times x plus 1, I can see that there's going to be 2 vertical asymptotes, one at x equals 2 and one at x equals negative 1. Alright. Along with vertical asymptotes, I will need to find any horizontal or slant asymptotes for this function. As you can tell, this function is bottom heavy, meaning that there will be a horizontal asymptote of y equals 0. Okay. Now I find the derivative. I'm done finding the asymptotes. I'm going to find f prime of x. To do that, I have to use the quotient rule, and I'm going to use this version of the function, the original version of the function, to find the derivative using the quotient rule. So the derivative of the top is just 3. The bottom, I just copied, x squared minus x minus 2, minus the top, which I didn't change, 3x minus 9, times the derivative of the bottom, which is 2x minus 1, all over the bottom squared, and I'm going to actually square the factorization of the bottom. So it's x minus 2 squared times x plus 1 squared. Alright, and that's the derivative. Once I simplify the top, expanding everything out, I'm not going to go through all of the algebra associated with that, but once I expand everything out, I get a factorization on top of negative 3 times x minus 5 times x minus 1, and the denominator is already factored. So that's my f prime of x. Alright, so based on this f prime of x, I need to find the stationary points, and I do that by setting f prime of x equal to 0. And when a fraction is equal to 0, that means that the numerator is equal to 0, but not the denominator. Alright? So that happens at x equals 5 and x equals 1. Okay? So here's what I'm going to do. Now that I have this information, I have my stationary points at x equals 5, so I'm going to put a dot there to show that that is a stationary point. And I have another stationary point at x equals 1. But if you remember, there was stuff happening at negative 1 and 2 as well, and those were vertical asymptotes. So I'm going to put my vertical asymptote here and my vertical asymptote here. Alright, and now that I've split up the domain using my stationary points and my asymptotes, I'm going to look at what's happening between these points. So this one was negative 1. Sorry, I kind of blotted that out. But if I look at any number less than negative 1 and I plug it in here, I'm just going to look and see what sign it is. So I will try negative 2. And if I have negative 2 minus 5, that's going to be negative. That negative 3 will always be negative. Negative 2 minus 1 will be negative. Anything squared will always be positive, so the denominator is always going to be positive. I probably don't even need to look at that ever again for the rest of this question. So I know that a negative times a negative times a negative divided by a positive is going to be negative. So what that means is before I get to this asymptote, the original function is decreasing. Alright. Then I look between negative 1 and 1. Well, I'm going to try 0. And negative 3 will still be negative at x equals 0. 0 minus 5 will still be negative. and 0 minus 1 will still be negative. So nothing really changed here. So I still have a negative first derivative, meaning that the function is decreasing before I get to x equals 1. Now let's try a number between 1 and 2, like 1.5. And remember, I'm only looking for what the sign is. So if I take 1.5, well, the negative 3 is always going to be negative. 1.5 minus 5 is negative, but 1.5 minus 1 is positive 1/2. So, and ignoring the denominator, because that's always positive, I see now that the first derivative between x equals 1 and x equals 2 is going to be positive, meaning that the function between x equals 1 and x equals 2 will be increasing. Now let's look between 2 and 5. Okay, let's try a number like 3. Well, negative 3 is going to be negative. 3 minus 5 will still be negative. 3 minus 1 will still be positive, and the denominator will be positive. So between 2 and 5, this function, the derivative is positive, meaning that the original function is increasing. All right, and then let's look after 5. Well, after 5, I can pick a number like 6. Negative 3 will still be negative. 6 minus 5 will be positive. 6 minus 1 will be positive, and the denominator will be positive, meaning that this entire derivative is negative, so the original function is decreasing. Okay, so I always split up my domain based on my stationary points and my asymptotes, and I look between all of those just to see what's going on. Now let's look at my intercepts. That's another thing I was asked for, x and y intercepts. There's my original function, and if I want to find the x-intercept, I'm going to set y equal to 0, set f of x equal to 0. And if a fraction is equal to 0, that means that the numerator is equal to 0, but not the denominator. And that happens at x equals 3. All right. And then to find the y-intercept, I'm going to set x equal to 0, so that's going to be 3 times negative 3 over negative 2 times 1. And that's going to be 4.5. All right, so all of that information is helpful to me. The stationary points, the x-intercept, the y-intercept, the asymptotes, everything has to come together in order for me to graph this. So here is a summary of everything that I've just figured out, and I've put it in the order in which it occurs. So let's graph everything as best we can. I've got the horizontal asymptote at y equals 0, so there it is. All right, and I've got a decrease. I'm just going to make a little note that before I get to this point, or this asymptote, x equals negative 1, then the function is decreasing. So I'm just going to draw a little down arrow there above the graph, just to kind of indicate that before I get to x equals negative 1, the function is decreasing. All right, and then I will draw my asymptote at x equals negative 1. There it is. All right, I know that the function, again, is decreasing between x equals negative 1 and 1. So I just put a little down arrow there again. And I know that in between x equals negative 1 and 1, I've got to pass through the point 0 and 4.5. 3, 4, 4.5. So I've got to go through that point and keep decreasing. I know that there is a local minimum at 1 and 3. So 1 and 3, it's got to go through that point as well. I got that 3 by plugging 1 into the original function. Whenever you find stationary points, always plug them into the original function to see where the y value is of that point as well. All right, then between 1 and 2, I am increasing for just a little bit. And I've got another vertical asymptote at x equals 2. So let me draw the vertical asymptote at x equals 2. Right there. And then I also know that it is increasing between x equals 2 and x equals 5. So I'm increasing again. And there is an x-intercept at 3, 0. So right here, there's an x-intercept there. It's the only one. There is a local maximum at 5 and 1/3. So right about there. It doesn't increase very much. And then after x equals 5, I'm decreasing. And I've got my horizontal asymptote at y equals 0 again, which I don't cross. All right, so how do I graph this? Well, if I need to decrease here and not cross the x-axis, because I only have one x-intercept, it looks like it's going to do something like this. It's just a sketch. So as long as you use all the information and don't create any new information, you're okay. Then between these two asymptotes, I've got to decrease to this point, decrease further to this point, and then increase. So it's probably going to look something like this. Make sure that that is a minimum. All right, and then after this asymptote, I've got to increase, pass through this point, pass through this point. So I'm going to do this. And then I'm going to have to decrease without crossing this asymptote. So it's going to not be much of a decrease at all. And that's what my function looks like. Okay? This takes a lot of practice and a lot of organization to do. So please email me any questions you have, and we will do some examples of this tomorrow. But please watch the other two parts of the video so that we can see what a quadratic over a quadratic looks like and what a quadratic over a linear looks like.